Good morning and welcome to the American Geophysical Union's fall meeting and the Earth at Night press conference. We have three speakers today, James Gleason, Christopher Elvidge, and Steve Miller. I'll turn it over to them, and after they make some opening remarks, we'll open it up to questions from journalists only. And also, if you want to get copies of the images that they're presenting today, the website for that is Earth Observatory, all one word, .nasa.gov/nightlights. / sorry, Harvey.
Morning, everyone. I'm Jim Gleason. I'm the Suomi NPP project scientist, and thank you all for coming out. We'd like to talk this morning and announce the release of the latest view of the Earth from space, one that highlights the new capability of the VIIRS instrument, measuring the visible Earth at night. And what I'm going to do is sort of give a brief overview of the Suomi National Polar Orbiting Partnership Mission, also known as Suomi NPP, and talk a little bit, just a quick review. As most of you know, we were launched in the early morning hours of October 28th last year in 2011. We've had a very successful first year and everything is operating normally. All the instrument data has been publicly released, and sort of our data highlight of the year is the National Weather Service is using the ATMS data now routinely to make weather forecasts. So we're all pleased with that. And what I'm going to do now is just give a quick overview of the satellite and what the instruments are, sort of work from front to back. On the back, viewing out the rear of the spacecraft is the OMPS instrument, Ozone Mapping and Profiling Suite. That was the data that was used this year to monitor the ozone hole, and a lot of you saw those interesting ozone hole pictures. Then followed by that on the right, in this case wrapped in the protective can there, is the Ceres instrument, the Clouds and Earth Radiant Energy Suite. This basically helps us understand the Earth's radiation balance, how clouds and the atmosphere reflect the solar energy, and monitoring that is a key global change question. Then the next two instruments on the left side there, the ATMS, Advanced Technology Microwave Sounder, and the CRIS, the Cross-Track Infrared Sounder. Those two instruments are the core of the weather forecasting suite, the sounder suite. Those working together measure the temperature and moisture profiles that are critical for doing the 3 to 5 day numerical weather forecast. And then the large box in the front is the VIIRS instrument, and we're going to talk about VIIRS today. VIIRS is a 22-channel imaging instrument that measures from the infrared, and that sort of picture on the top left there is some very interesting details in the sea surface temperature off Greenland. In the visible, in the sort of lower left, that's a pretty standard RGB picture of Superstorm Sandy, and what's sort of interesting there you can see is the amount of sediment and material that's been churned up by the waves off the coast of Florida. And then the new capability that we are talking about tonight, which is the ability to measure visible light at night, and that's a nice picture of India in the day-night band, and we will hear more about that. Most of you have seen this image earlier this year, and this morning we're going to present a greatly improved view of the Earth at night, sort of our VIIRS black marble. And to hear more about the VIIRS instrument and the day-night band, we have Chris Elvidge from NOAA.
Good morning. My name's Chris Elvidge, and I work at NOAA's National Geophysical Data Center in Boulder, Colorado. And it was my team that processed 2 months of VIIRS day-night band data to make a global cloud-free composite that we passed over to the NASA team that wrapped it around the globe to make the black marble. And 2 of my team members are here. Misha Zishin is worked on the terrain correction for the day-night band data that was processed, and David Su is worked on the cloud detection algorithm. And so there are different types of surface lighting that can be detected by a satellite. There are the lights from cities and towns that we're all familiar with, but also there are places that there are no people living, but there are still lights, such as an industrial site, that get detected. With this capability, it's very easy to detect gas flares and fires, but also heavily lit fishing boats. And so these are not the typical boat that might have a few running lights. These are boats that are actually using lights to attract their catch. And for 18 years, my group has been working with data from the Air Force Defense Meteorological Satellite Program, an instrument called the Operational Line Scan System. We've made nighttime lights products, global cloud-free composites. We have a time series that's available at our website. And starting in April, we began to work with data from the VIIRS instrument. And it's important to remember that in both cases, these instruments, the low-light imaging was designed for the meteorologists. It's there to enable the detection of moonlit clouds. And so we can use the data for nighttime lights, but these instruments they're not really optimized for nighttime lights. I'm pretty sure that someday there will be an instrument that is optimized for nighttime lights. But in the meantime, we make as much mileage out of these data sets as we can. And here's a look at side-by-side of the new data from VIIRS. This is from our cloud-free composite that's from 2 months, April and October 2012, of the San Francisco Bay Area versus the corresponding product from the old satellite. And one of the things you'll notice is that the old satellite data, there is saturation because of the limited dynamic range and 6-bit quantization, and the fact that the gain is turned up very high. So you don't really know how bright it is in those white areas. You know that there's lights there, but you can't tell what the brightness level is. We can with VIIRS. There's no saturation. Plus, with the improved spatial resolution, there are a lot of details and features that we can find in the VIIRS data that are either missing or very ill-defined in the old type of data that we have had for many years from DMSP. In terms of scientific applications, these global products are used as proxies for variables that are difficult to measure directly on a global basis. So for instance, they're used to model population distribution, the distribution of economic activity, fossil fuel CO2 emissions, and a number of other variables that scientists have taken the data and developed their applications from these nighttime lights data sets. The lights are also used directly for things such as assessing astronomical viewing conditions, basically how much light is coming back down towards the Earth out of the sky, artificial sky brightness, which obscures astronomical features. And so they have been used that way. They've also been used for site selection for astronomical observatories. They're being used in ecological studies, looking at the impacts of artificial lighting on species of birds and insects. And actually, they're also being used in human health studies. They have also been used for detection of power outages. And the basic concept is that if you know where there should be lights, you can look at an image after an event and see if the lights are present or not, or whether they're dimmed. And this is an example from an event that hit the East Coast last spring, where lights were dimmed and some lights actually went out following a serious set of storms. We've also used the data to look at gas flares, and here's a cluster of gas flares in North Dakota. And so for many years we've used the global DMSP data to estimate gas flaring in 65 different countries. And so we're now working with the VIIRS data to make some better assessments of gas flaring. And here's the example for fishing boats. Here's the Sea of Japan and Bohai Sea or Yellow Sea. Here's Korea. Japan, China, and offshore there are clusters of points of light that are actually fishing boats, large vessels that are using heavy lighting to attract their catch. One thing to notice here is that the North Korea's got very few lights. Interesting. So what makes VIIRS better than DMSP? Well, one of the big factors is spatial resolution. And so DMSP, even right underneath the spacecraft, the footprint is a 5 kilometer by 5 kilometer box on the ground. And it gets larger as you go out to the edge of scan. For VIIRS, that footprint is 742 meters square on a side. And that's true from nadir, which is right underneath the satellite, all the way out to the edge of scan. And so the VIIRS instrument was very carefully designed to maintain this spatial resolution constant from right underneath the satellite out to the edge of scan. And so it is very high quality data and substantially better spatial resolution. I rated it 6 times better spatial resolution. Other things that make VIIRS better is that we have more bit depth. We have 14-bit resolution on this day-night band data from VIIRS. DMSP, believe it or not, was 6-bit data. 6 bits, that's 0 to 63. That's all we have to work with from DMSP. Also dynamic range. Due to limited dynamic range, the DMSP data saturate on bright lights in the operational data collections, and we don't have that problem with VIIRS. The VIIRS data, we can really call it quantitative because it's well calibrated in flight, and for DMSP, there is a pre-flight calibration, but no in-flight calibration, and we know that sensors degrade over time. The final factor that makes VIIRS better is the fact that it's multispectral. So we have additional spectral bands that we can use to look at combustion sources to help discriminate which lights are associated with electric lighting versus flames. And also we have all the infrared bands that help us to better characterize the optical character of clouds. So here's the product that NASA put together. They called the Black Marble. The nighttime lights came from my group. It's a rectangular image that's about 80,000 pixels wide and about 40,000 pixels high. We passed it to our NASA colleagues, and they wrapped it around the Earth to make this product, which is available at their website. In summary, the VIIRS day-night band provides substantial improvements over the DMSP nighttime lights in terms of spatial resolution, detection limits, dynamic range, and quantization. We've discovered that the basic processing steps that we use for constructing DMSP nighttime lights products, that is the global cloud-free composites, that basic set of steps can also be applied to the VIIRS data. And what we anticipate is that there will be the improved nighttime lights products from VIIRS will lead to advances in all the application areas that were demonstrated with DMSP data. With that, I'll pass it on to Steve Miller.
Sorry, a little excitement.
Good morning. I'm Steve Miller. I work at Colorado State University in the Cooperative Institute for Research in the Atmosphere, CIRA. So for all the reasons that Chris mentioned just now, given that the low-light satellite technology has been up there for 40 years, for all those reasons and more, the VIIRS day-night band is truly a paradigm shift in the technology and capability. So this is not your father's low-light sensor, and I'll try to show on the next few slides evidence for that. But first, let's start with just a discussion, a high-level discussion of what we can do with the nighttime lights. And this is just not a visible sensor like in the day. We have all other kinds of information at night. We've already talked about some of the anthropogenic or man-made light sources. But think of all the other things that we can see at night. Fires, lightning flashes. When the moon's not up even, we have emission sources within the atmosphere from these various sources, Aurora. Now we bring in the moon, and it's almost like a surrogate for the sun. It's reflecting off of clouds. It's reflecting off of smoke, snow cover, volcanic ash. These are the kinds of things that we can do uniquely at night with the day-night band. So let's just start with an example of Chris mentioned the power outages and power recovery analysis. Well, unfortunately, we've had a recent example of this with Superstorm Sandy making landfall in late October. So when we look at a difference plot between before and after lights, and we've color-coded this in a way where the red denote power outages and the gold areas where the power stayed on, you can see as we zoom into the New Jersey, Long Island area, lots of red areas on November 1st, just after the storm made it through. And then a few nights later, you can see some of those lights recovering, some of those red areas going away and turning gold. Then we go another few days and it's recovered quite a bit, although there are still some red areas. So this is the kind of thing that we can do with difference imagery just based on some of Chris's products. If we go ahead and zoom in a little bit on New York City, now we're sort of pushing the spatial resolution limits of the imagery quality here at 742 meters, but you really can see the outage in lower Manhattan area. And if we take an aerial photo, this is what it looked like from the sky near the ground. And even at the 742 meter resolution, you can actually see that One World Trade Center at this time is lit up. You see a little bit of gold in the lower Manhattan area. So we're truly getting into the fine scale details of power outage and power recovery. Well, it was a devastating season for fires across the U.S. We're in the middle of this drought, and over northern Idaho, there was a huge complex of fires. Where there's smoke, of course, there's fires. Where there's fires, there's going to be nighttime lights from those flames. And so that's what we're seeing here. As you toggle back and forth, pick your favorite smoke plume, and you can see associated with it a light source from the fire. So if we zoom in a little bit here, we can see the Mustang Complex fire and some of the lights coming from those flames. We also see in this example smoke, which is in this case being illuminated by the moonlight. Now realizing that smoke is very difficult to see at night in thermal infrared bands. So this is moonlight bringing that information forward. Let's talk about the moon for a moment. As we go through the 29.5-day lunar cycle, we see a lot of different brightness levels. This is looking, of course, over Saudi Arabia, Iran region with a full moon. Notice the bright land surfaces, a lot of deserts in this area highly reflecting. As we transition into gibbous and going into the crescent moon and finally new moon, we see how this brightness changes. So this is information across the lunar cycle that we can exploit for various things in the atmosphere. Here's some clouds illuminated by moonlight off the California coast. We see some interesting black features to the east of these clouds, and in fact, those are cloud shadows being cast by the moon, which is in the western skies. So you're almost looking at a three-dimensional view of the clouds here, the high and lower cloud deck that it's illuminating. So these are marine stratocumulus off the coast of California. If you zoom in to the Salinas Valley area, you can actually see that fog creeping up into the valley. You can actually see some fine-scale details of the fog getting into the valley as well. So this is the kind of thing that we can really take advantage of with low-light imagery, realizing that sometimes this fog has a very similar temperature to a cold background of land that doesn't have fog over it, so we can actually discriminate that fog in higher detail with the day-night band. If we go to high latitudes, around this time of year, we don't have much light whatsoever, visible or otherwise, up at 70 degrees north and above. We're in the great darkness, as they call it up there right now. And so the moonlight can really help in this case, bring out features such as sea ice. We had a record ice melt over the past summer, and now we're going to be building that ice back up over the winter months. But with the thermal infrared, we can see things like clouds and some surface features, but it's sort of hard to bring out the subcloud features like the ice and the snow. We toggle between the thermal infrared and this low light imagery, and we begin to see some structures, especially the sea ice up here. Oops. The sea ice up here, you can see that. Now we'll zoom in on the snow cover region. Thermal infrared, you can't really see it. It's the same temperature as the surrounding non-snow covered surfaces, but now you bring in the moonlight reflection and you see those dendritic features popping out from the moonlight reflection. You can see the valleys that don't have snow in them. So this is the kind of information at high latitudes up in Alaska and the South Pole during its winter, where the low light imagery is particularly useful. Staying up in the high latitudes in the Kamchatka Peninsula, well, Dave Schneider from USGS just gave me a heads up last week that the Tolbachek volcano was erupting, and so we went in and looked at the eruption in progress. And in this case, we are looking at the night before the eruption. I'm just pointing out here with the arrow where the volcano is located. Now with the eruption, we see this explosion of light. Even under overcast conditions here, that light scatters right through the clouds, a visible light does. And then the next night, we can see it as well. So this is literally the light from the magma, the lava flow coming off of the volcano that we can see. So this is a unique capability of the day-night band that can help monitor the volcanic activity in all weather conditions, in fact. And the Aurora, of course, at high latitudes, we can see as well from their extreme light emission. We can see these structures all the time in the high latitudes. If we zoom in on these two areas here, you can notice that in the image on the left, where there was not as much auroral light, we don't see that ice edge. There's no moonlight in this imagery, so the only sources of light could be from the aurora. Whereas near the aurora illumination, you can see that ice edge pretty well. So this is kind of an interesting segue into the next part here. We're looking from the International Space Station at a view. And this is not a star, this is actually the moon. They've cranked up the gain so you can see things. But here's the aurora. And you see this other limb of light, and that's not aurora. That's going to be a global source of light. It's called night glow. Airglow is the more general term, but it's chemical reactions in the upper atmosphere that produce this rim of this veil of light. It's a very thin layer in the atmosphere. But when you look toward the limb, you can see it. Here's what it looks like from the surface. We have starlight, of course, and this airglow or night glow that looks like a rim of light. It's somewhat pan-horizon sort of illumination source. And we've discovered by accident that the day-night band is actually sensitive enough to detect these kinds of sources of light and take advantage of them on completely moonless nights. So when you think about that now, not only do we have a low-light imaging capability at night when the moon is up, but now we have an additional source of illumination that we can take advantage of with the day-night band. This really hits at home here in this image where we have the regular lights that you would expect to see from North America, East Asia, Australia. This is over the Pacific Ocean now. All these features that you see here are clouds reflecting that night glow. And even in some areas, you can see the illumination from the night glow itself. Now, the night glow is an understood phenomenon, but we did not anticipate that we'd be able to exploit it for meteorological purposes with the day-night band. So these areas where we see clouds, we weren't expecting to see clouds. We were trying to characterize the noise in the sensor, and we found something entirely different and pretty extraordinary. So why is this important? Well, going back to the idea that thermal measurements that we traditionally have at night have difficulty distinguishing between things of common temperature. Well, with reflectance at night, we talked about that with moonlight, but now with night glow, we can actually bring out structures that we couldn't before, such as this low cloud deck off the Korean Peninsula. We can see the edge of it on the eastern side, but now with the night glow, we can actually bring out that western edge as well, quite well. Another example is talking to the coupling between the lower atmosphere and the upper atmosphere. We need to understand the whole system in a holistic way to make best use of our knowledge for climate and climate change. Well, these kind of measurements help us with that, we think. In this case, we have thunderstorms over Texas that are basically pumping energy up into the upper atmosphere. That energy propagates upward and it breaks, and we can actually see that at the mesopause, about 50 miles up in the airglow. This is an airglow image corresponding to this IR, and if you look really closely, you can see these waves. They almost look like ripples, and so that energy is coming up, propagating outward, and you see these ripples being forced. It just so happens that we got lucky, and we had a surface observation in eastern New Mexico that was looking toward the east with a low-light camera, and they recorded this movie of these same waves in the upper atmosphere propagating to the north. So you can see those waves. These are airglow waves now propagating northward from the storms over Texas. So just a really nice example of, I'll play that one more time for you. A really nice example of a surface validation of a really fantastic kind of observation that we now have from the VIIRS day-night band. So the highlights are to keep with the theme of this low-light imaging, perhaps the low lights. The night is not really that dark as we see. It's all kinds of sources. It's replete with sources. And there's significant advances with the day-night band over the operational line scan system. We've only really scratched the surface on the capabilities of the sensor. And as we've seen in the last several slides, in fact, there's new frontiers of research right here and discoveries to be made. So thank you again, and I'd like to thank NASA really for hosting this at AGU and providing me an opportunity to share this exciting news with you guys. Thanks.
We'll take questions now for a few minutes.
Hi, Randy Shostak, reporter with EOS at the AGU. Does it surprise you to have so many applications for the VIIRS data? And I wonder if you can also give a hint at some of the additional possible applications. And also if you can expand on how this data is being used for human health studies.
I'll respond on the human health studies. There have been several teams around the world that have used nighttime lights data to look for correlations between lighting levels and disease incidence. And what they're trying to tease apart from the data is whether there's any human health effects associated with living in areas where there is intense lighting. And of course, there's lighting inside people's houses, but there's also lighting outside. And it's quite bright in city centers. So right now, we're working with a team at the University of Connecticut that is examining the incidence rates for breast cancer and lighting levels at a county level and sub-county level in Connecticut. And there's a team at a university in Israel that's also done research in this area. The other health issue that has been investigated along these same lines is cardiac disease. And so those are the two that I'm aware of.
Other questions?
In terms of the additional uses for the day-night band, I think that we've really been pleased with its performance to this point. We're impressed with its abilities. We did know, based on the operational line scan system legacy sensor, certain capabilities it would be able to do. But to actually see this in higher resolution, to see this in quantitative detail, and be able to actually do scientific applications with the data, this is a new ground for us, I think. You know, with the airglow examples at the end there, I think this is a new frontier for science in the low-light imaging realm for meteorological purposes. So there's been some discoveries in the past as well about bioluminescence that we can see from low-light visible. With the OLS we used it for. We haven't seen the same feature yet with the day-night band, but we're looking. So I think that there indeed will be many new applications that we can do. That's what makes this such an exciting measurement.
Questions?
Ryder Miller, freelance. How do you factor out the normal light that's produced and get passed to specific sources?
Well, the only discrimination that we're able to do at this time is between electric lighting and lighting that's associated with combustion sources. That is basically open flames from gas flares or forest fires. And so there are spectral differences between different lighting types. And so in some cities you see a lot of amber lights, and those are high pressure sodium. And in other places, there's a lot of these bright, kind of almost blue-white lights. Those are metal halides. And there are spectral differences between those different light sources. But the VIIRS spectral band that does this low-light imaging is very broad. It's all acquired together. And so you don't have the multispectral information that would enable discriminating different lighting types. But we are able to distinguish electric lights from lighting that's coming from combustion sources. And we do that by bringing in some of the other spectral bands that are collecting data at night from VIIRS.
You can also bring in the context of space and time variability. For example, lightning flashes can be detected with the day-night band, and those are always going to be correlated, of course, with thunderstorms, and so and they're very ephemeral, changing quickly. So those kind of features we can differentiate readily from other sorts of surface lighting.
Any other questions? Oh.
Paul Doherty from the Exploratorium. I always thought that the airglow was about equal in brightness to the starlight. What is the actual contribution from starlight?
It's not negligible, but my understanding is that with the airglow, it's about a factor of 10 brighter. And it's simply because of the location of the sensor response for the day-night band being into the more toward the red and the near infrared, and you're getting into hydroxyl emission lines in the airglow, and so that becomes a stronger source than we would see visually with our own eyes. So yeah, it's a significant source of light and at that part of the spectrum we're finding.
Well, great. Well, thanks to our panel. Our next press conference will be in here at 11:30 on the latest results from the Arctic. Thanks so much.